The Great Barrier Reef is often described as one place, but it is better understood as a vast network. It includes more than 2,900 individual reefs and around 900 islands spread across roughly 2,300 kilometers along the Queensland coast. That scale matters, because the reef is not a single uniform habitat that responds the same way everywhere. It is a patchwork of environments, each with different exposure to temperature, currents, storms, and human activity. This is one reason reef headlines can sound contradictory. One region may be recovering while another is deteriorating. Both can be true at the same time. Seeing the reef as a giant, varied system is the first step to understanding both its resilience and its vulnerability. What makes this structure extraordinary is that it is built by tiny animals called coral polyps. A single polyp is small and soft-bodied, but collectively they create hard limestone skeletons that accumulate over long timescales. Layer by layer, generation by generation, these skeletons form the complex architecture of reefs. That architecture then becomes habitat for thousands of other species, fish, mollusks, crustaceans, sea turtles, and many organisms that are still being studied in detail. In effect, the reef is both builder and building. Living corals construct the physical framework, and that framework supports one of the most diverse marine ecosystems on the planet. When coral structure declines, biodiversity does not just shrink in number. The entire ecological choreography of feeding, shelter, breeding, and migration becomes less stable. The reef's global fame comes from both science and symbolism. It was inscribed as a World Heritage Site in 1981 and repeatedly recognized as one of Earth's great natural wonders. It is also widely known as the largest structure made by living organisms, visible from space under favorable conditions. But recognition can create a dangerous illusion that importance guarantees safety. It does not. International status brings visibility, tourism, and political pressure, yet ecological outcomes still depend on hard constraints: water temperature, water quality, and disturbance frequency. A famous ecosystem can decline just as rapidly as an obscure one if those conditions move in the wrong direction. So the reef's iconic status should be seen as a responsibility, not a shield. Admiration is not protection unless it translates into effective action. Protection frameworks do exist, especially through the Great Barrier Reef Marine Park. This has helped manage fishing pressure, tourism behavior, and other local impacts across large areas. Marine zoning, enforcement, and monitoring can reduce direct human damage and give stressed habitats better odds of recovery. But marine parks are strongest against local pressures, not global heat. A boundary line cannot stop warm water from spreading during marine heat waves. That is the core policy tension. Local management can buy resilience, but it cannot cancel climate physics. The smartest conservation approach is therefore layered. Reduce what can be controlled locally, while also pushing broader climate mitigation that reduces long-term thermal stress. Treating these as competing strategies is a mistake. The reef needs both at once, and over decades, not just election cycles. Several pressures hit the reef simultaneously. Some are chronic, such as runoff carrying sediments and pollutants from land-based activities. Poor water quality can reduce light, stress coral physiology, and alter ecological balance. Other pressures are biological, including outbreaks of crown-of-thorns starfish, which feed on coral tissue and can strip reef surfaces at scale when populations surge. Then there are acute thermal shocks, periods of unusually warm water that trigger mass bleaching. These stressors do not operate in isolation. A reef weakened by one pressure often becomes less capable of resisting another. That compounding effect is central to modern reef science. It is rarely one single cause and one single collapse. It is a web of interacting pressures that together push parts of the system past recovery thresholds. Coral bleaching is one of the most visible outcomes of heat stress, but it is often misunderstood as immediate death. Bleaching occurs when corals lose the symbiotic algae that provide much of their energy and color. Without those algae, corals turn pale and become energetically compromised. If temperatures return to tolerable ranges quickly, some corals can recover. If heat persists or repeats, mortality rises sharply. This distinction matters because bleaching is both a warning signal and, at times, a pathway to death. Public discussion often flips between panic and minimization, but the truth is conditional. Severity, duration, and recurrence determine outcomes. A single bleaching event can be survivable in many areas. Repeated events with short recovery intervals are far more dangerous, because they deplete the reef's biological reserves. Long-term studies have reported major declines in coral cover over recent decades, with analyses showing losses exceeding half in certain measured periods. Coral cover is not a perfect metric, but it is a critical one. It tracks how much living coral physically occupies reef surfaces, which strongly influences habitat complexity and reproductive potential. When cover declines, reefs often become flatter and less structurally intricate, reducing shelter for many species and changing predator-prey dynamics. Importantly, not all coral species decline at the same rate. Some are more heat-sensitive, others more storm-sensitive, and others recover faster after disturbance. That uneven response can reshuffle reef composition over time. So even if total cover later rises, the reef that returns may function differently from the reef that was lost. The 2016 and 2017 bleaching events were pivotal because of their scale, especially across long northern stretches. These were not isolated local anomalies. They reflected broad ocean warming conditions severe enough to produce widespread stress. Another mass bleaching event confirmed in 2022 reinforced concern that such events are becoming more frequent. Frequency may be the most important variable of all. Reefs can recover from shock, but recovery requires time for surviving adults to regain health, reproduce, and rebuild structure. If major heat events recur too quickly, that cycle is interrupted. This is how systems shift from episodic damage to chronic decline. It is less about one catastrophic moment and more about repeated shocks arriving before biological recovery catches up. In that regime, resilience steadily erodes even when some patches still look healthy. One especially concerning finding after repeated bleaching was a sharp drop in coral recruitment, meaning fewer juvenile corals entering the system. Recruitment is the bridge between present damage and future recovery. If mature breeding colonies are heavily reduced, larval supply falls, settlement slows, and regrowth potential weakens. Scientists also observed changes in which coral groups were reproducing successfully, indicating a deeper ecosystem reorganization. Reorganization is not automatically collapse, but it can reduce diversity and alter function. Fast colonizing species may expand while slower, structure-building species struggle. Over time, that can produce reefs that retain coral presence but lose complexity and stability. In practical terms, the question shifts from will there be coral, to what kind of reef will remain, and how well will it support biodiversity and coastal economies. At the same time, monitoring has shown periods of substantial recovery, including strong rebounds tied to fast-growing acropora corals in recent survey years. This is real and important. It proves the reef still contains powerful regenerative capacity. But recovery headlines need context. Fast-growing corals can rapidly increase cover, yet they may also be vulnerable to future bleaching, storms, or predation. So a rebound in one indicator does not erase long-term risk. Think of it as an ecosystem capable of bouncing back, but not guaranteed to keep bouncing forever if shocks intensify. The most responsible reading is neither hopeless nor complacent. The reef is not dead, and it is not safe by default. It is dynamic, responsive, and increasingly dependent on whether disturbance intervals allow recovery processes to complete. Beyond ecology, the reef is deeply human. It has long-standing cultural and spiritual significance for Aboriginal Australian and Torres Strait Islander peoples, whose relationships with sea country are intergenerational and place-based. It is also economically central to coastal Queensland, with tourism generating billions annually and supporting regional jobs. That dual significance changes how we frame decisions. Conservation is not simply about preserving scenery for visitors. It is about cultural continuity, food webs, livelihoods, and long-term regional stability. If reef health degrades, economic systems linked to tourism and fisheries face compounding risk. If management improves and climate pressure is reduced, those same systems gain resilience. The reef's future is therefore not a niche environmental issue. It is a test of whether ecological stewardship and economic planning can be aligned at meaningful scale. So where does this story point next? The reef's trajectory depends on three connected layers: global climate trends, local management quality, and biological recovery capacity. Global warming sets the thermal baseline. Local governance influences water quality, extractive pressure, and habitat disturbance. Biology determines whether surviving corals can reproduce, recruit, and rebuild before the next shock arrives. None of these layers can be ignored. Strong local policy without climate progress is insufficient. Climate progress without local stewardship leaves avoidable damage in place. And both are weakened if monitoring is poor and warning signals are missed. The Great Barrier Reef remains one of Earth's clearest indicators of planetary change, still alive, still adaptive, but increasingly constrained. Its fate will not be decided by a single event, but by sustained choices made repeatedly over time. If you found this helpful, please like this video and subscribe for more explainers.